Let us begin our discussion of section 3.1, Algebraic properties of solutions of linear systems. In this section, we are talking about systems of differential equations. Please take a look at this. On the left-hand side, we have x1 prime, x2 prime, and so on xn prime. On the right-hand side, we have some functions on t, x1, and so on xn. Now, x1, x2, and so on xn are not variables. These are functions. x1 is a function on t, x2 is a function on t, and so on xn is a function on t. Next, if in addition we have initial conditions, initial condition number 1, number 2, and so on number n, this in combination with this is called the initial value problem. This section consists of 3 parts. In part 1, I'll show you how to convert a single differential equation into a system of differential equations. In part number 2, we will discuss some basic definitions from linear algebra. In part number 3, we will discuss how to solve systems of differential equations. Important. Here we are talking about systems of first order differential equations only. Now, part 1. How do we convert a single equation into a system of first order equations? In order to do that, we need these formulas. So here's what we do. Over here, we have a second order differential equation. In general, if we have an equation of order k, we use first k formulas from this list. In our case, k is 2. We have second order equation. In order to convert it into a system of first order differential equations, we use first 2 formulas from this list. Note that this is formula number 1 and this is formula number 2. Here's what we do next. We start with formula number 1. We take the derivative of the left-hand side and of the right-hand side. Done. Note that according to formula number 2, this, which is over here, is equal to this, which is over here. Conclusion, x1 prime is equal to x2. This is equation number 1 of our system. It's over here. Question is, how do we come up with equation number 2? In order to come up with equation number 2, first we take the derivative of both sides here. Done. Note that derivative of first derivative is second derivative of 1. Here is what we do next. We go back to the given equation. We move these 2 terms to the right. Next, divide both sides by 4. Note that since we put minus in front of the whole fraction, this minus becomes plus. And now let us use both formulas. By this formula, y prime prime, which is over here, is equal to x2 prime. Done. By this formula, y prime, which is over here, is equal to x2. Done. Lastly, by this, y is equal to x1. We replace y by x1, and this is the second equation of our system. Now y is completely gone. We have only x1 and x2, and indeed the left-hand sides of each equation are of this form, and on the right-hand side we have some functions on x1 and x2. Folks, any questions?
So how do you know to set x1 to be y and x2 to be dy dt like originally?
Once again, this is given. Note that we can denote y prime. Y prime is a function. We can denote y prime by whatever. For example, let us denote y prime by x2 of t. Let us denote y prime prime by x3 of t, and so on. Let us denote y by x1. Here we just use a different letter. Instead of y of t, we put x1 of t. You see what I mean?
Yeah, I do. I just didn't see the top part where they have all that.
Any other questions?
Yes. If you can tell us why sort of we're doing this.
Excellent question. Question is, why do we convert a single equation into a system of differential equations? It turns out that there is a relationship between the general solution of this equation and the general solution of the system. One can convert the general solution of this equation into the general solution of the system, and vice versa. Here's one of the reasons. Was that your question?
Yes, sir. Thank you.
Next, let us consider the following general example. Here is a linear homogeneous equation of order n. Let us convert it into a system of n first order equations. Step 1, copy these formulas. Here's formula number 1. It's over here. Formula number 2, it's over here. And so on. The last formula is over here. This one. But now, question is, what do we do over here? How do we come up with these formulas, and why do we need it? Well, note that y is equal to x1. If we replace y here by x1, we get this. And now this is the first equation of our system. It's over here. Next, second derivative of y is derivative of first derivative. But according to what is written here, y prime, which is over here, is x2. We replace this by x2, we get this. x3 is equal to x2 prime is this second equation of our system. It's over here. And so on. xn is equal to the derivative of order n minus 1 of y, but the derivative of order n minus 1 is derivative of order n minus 2. We replace this by x subscript n minus 1. Xn is equal to xn minus 1 prime. This is this equation. So our formulas that are written over here give us first n minus 1 equations of our system. Question is, how do we come up with the last equation? Well, in order to come up with the last equation, we go back to the given equation. Here it is, I copy it here. We move these terms to the right, done. We divide both sides by an, done. And now we put minus in front of the whole fraction. Therefore, all these minuses become pluses. And lastly, according to what is written here, we replace this, and so on this by xn, xn minus 1, and so on x1. And according to what is written here, we replace nth derivative of y by xn prime. By the way, how do we come up with this? Nth derivative is derivative of the derivative of order n minus 1. But according to this, which is over here, is equal to xn. We replace this by xn, the result follows. So nth derivative of y is equal to xn prime. It's exactly how we jump from here to here, and this, which is over here, is the last equation of our system. Folks, any questions here?
So essentially, it's just plugging in the values.
Well, once again, these equations follow from these formulas. In order to come up with the last equation, not only we use these formulas, but also the given equation. Was that your question?
Yes, thank you.
Other questions?
Professor, can you repeat again how you were able to change d to the n ny over dt to the n to what you have after?
Are you talking about this formula?
Yes.
So you asked me how we jump from here to here, correct?
Yes.
Here's what we do. Derivative of order n is derivative of the derivative of order n minus 1. Agree?
Yes.
Know that this is same expression, right?
Mm-hmm.
According to what is written here, this is equal to xn. Replace this by xn, we get this. Agree?
Okay, I understand. Thank you.
Other questions?
Can you explain what you did again with the a sub n?
Yes. So first we move these terms to the right and switch the sign. Instead of pluses, we get minus. And then divide both sides by this. Done. Was that your question?
And the an was just from like the original given equation, correct?
Note that this is a copy of this. It's same thing.
Okay, thank you.
Last example. Over here, note that number 1, now we have a non-homogeneous equation. Number 2, non-linear, because here we square y prime. Moreover, in addition, we have the initial value problem. What do we do? Again, we apply same approach. Since we have an equation of order 3, we use 3 formulas from the list that give us two initial equations, equation number 1 and equation number 2. These equations are over here. How do we come up with equation number 3? Here's what we do. Let me first copy this over here. We move this term and this term to the right. Done. And now let us replace y, which is over here, by x1. Done. And y prime, which is over here, by x2. Done. Lastly, we use this in order to replace third derivative of y by x3 prime. This is equation number 3. By the way, let me make the following general remark. It is easy to remember first n-1 equations of our system. Here x1, then x2, then x2, x3. Over here, same thing, x1, x2, x2, x3, and so on. But I encourage you to do the whole procedure because we need these formulas in order to come up with the last equation. Anyways, here is our system, but now we have to come up with new initial conditions for x1, x2, and x3. How do we do that? We go back to these formulas. According to this, since x1 is equal to y, y of 0 is equal to x1 of 0. It's exactly what is written here. But by this, y of 0 is 1. We put here 1. Next, according to this, y prime is x2. Therefore, y prime of 0 is x2 of 0. But y prime of 0 is 0. Or we put here 0. So x2 of 0 is 0. In the same way, we come up with condition number 3. x3 of 0 is equal to 0. So here is our system, and here are conditions. Condition number 1, we skip this. x1 of 0 is 1. Condition number 2, we skip this. x2 of 0 is 0. Condition number 3, we skip this. x3 of 0 is 0. Folks, any questions here?
Oh, wait, Professor, could you explain how you're getting the 3 values again?
3 values, are you talking about this, and this?
No, I'm talking about the one in the bracket.
Are you talking about this?
Yeah.
How we come up with this?
Yeah.
So, these two equations are always same. Note that what is written here is a copy of this. In order to come up with these equations, we start with these formulas. Since our equation is an equation of order 3, we use only 3 initial formulas from this list. So here, formula number 1, formula number 2, and formula number 3. Now, since y is x1, replace y by x1, we are done. x2 is x1 prime is formula number 1. Next, x3 is y prime prime, but y prime prime is y prime, the whole thing prime. However, y prime is x2. We replace this by x2. Here is the result. x3 is equal to x2 prime is equation number 2 of our system. Lastly, in order to come up with this, we start from the original given equation. It's same as this. We move these two terms to the right, done, and then we replace y by x1, thanks to formula number 1. We replace y prime by x2, thanks to formula number 2. And we replace y prime 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 by x3 prime, thanks to this. Did I answer the question?
Yep, it is. Thank you.
Okay, we are done with part 1. Now part 2. In this course, we will discuss a particular case of such systems. It's over here. This is a particular case of system number 1. Now let us talk about terminology. If all these g's are equal to 0, we call such a system homogeneous. If at least one of these g's is not equal to 0, we call such a system non-homogeneous. So it's a little bit confusing, because if we have a single equation, we say that our equation is homogeneous if the whole right-hand side is equal to 0. Here we are talking about these portions only. However, note that if we move this to the left, this to the left, and so on, then on the right we'll get only G1, G2, and so on, Gn. So if all these g's are equal to 0, the system is homogeneous. If at least one is not equal to 0, non-homogeneous. Next, let us talk about subscripts. Guys, this is not 11. This is not 21. This is not 22. These are so-called double subscripts. The first number gives us the row. The second number is the column. So over here, A subscript 1, 2. First row, second column. This term is in equation number 1 and in column number 2. Is what we do next. In most problems in this course, we will discuss only a particular case of such systems, namely homogeneous, first order, linear systems of differential equations with constant coefficients. Means all these A functions are constant functions. It's over here, constant, 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 and so on. Next step. It turns out that we can rewrite any such a system in a compact, concise way. Here it is. Please take a look at this. Boldface x dot is equal to ax. I claim that any such a system, this is a copy of what is written here. So once again, I claim that any such a system can be rewritten as boldface x dot is equal to ax. Question is, what is boldface x? What is that? What is capital A? Here are the explanations. First of all, by a vector, we mean the following array with one column and n rows. x1, x2, and so on, xn. If these x's are functions, we put here boldface x of t, and here x1 of t, x2 of t, and so on, xn of t. And now, the derivative of x is this. We denote it by either this or boldface x dot of t. So we answer question number 1. Over here, boldface x dot is the following: x1 prime, x2 prime, and so on, xn prime. Next, what is a matrix? A matrix is an array with m rows and n columns. And again, we use double subscripts. For example, here a subscript m1 means this is from mth row and first column. Next question is, what do we mean by A times X? In order to find the product, we use a so-called row-column rule. Here's what I mean by that. In order to multiply A by X, first we multiply this row by this column. Then we multiply second row by this column, and so on, last row by this column. But how do we multiply a row by a column? Here are the formulas. In order to multiply this row by this column, we multiply A11 by x1, A12 by x2, and so on, A1n by xn, and then we add these terms together. A row times column, here is the result. Second row times this column, here is the result. And so on. A last row by this column, here is the result. Example, here is matrix A, here is X, a row, column, expression number 1, a row, column, expression number 2, a row, column, expression number 3. Let me make 2 remarks. Number 1, we can multiply A by X only if the number of columns in matrix A is equal to the number of rows, the number of components in vector X. For example, if in this matrix, instead of 4 columns, we have either 3 columns or, say, 5 columns, we cannot multiply such a matrix by this X. However, if instead of 3 rows we have 4 rows or 5 rows or 2 rows, we can perfectly multiply such a matrix by X because the number of columns is same, 4. Remark number 2. When we multiply A by X, note that X is a matrix column, means it has n rows but only one column. When we multiply A by X, the resulting matrix is a matrix column again. This expression is long, but this is a single expression. It's not like we have here column 1, column 2, and so on. No, we have only one column here. Component number 1 is this, component number 2 is this, and so on. Component number n is this. So when we multiply A by a matrix column, the result is a matrix column again. And now let us go back to our system. How come that this system can be rewritten in such a concise form? By the way, we can skip this. So x dot is equal to ax. Well, here's why. X dot is this. This is the left-hand side of our equation. Ax, according to what is written here, is this. So on the left-hand side, we have a matrix column. On the right-hand side, we also have a matrix column. Moreover, both matrix columns have same number of rows. And it is known that two matrix columns are equal if and only if the corresponding components are equal, which means this is equal to this. It's indeed equation number 1, and so on. This is equal to this. It's indeed equation number n. So, in fact, what is written here can be rewritten in the following concise form. Boldface x dot is equal to ax. For example, please take a look at this system. This system can be rewritten in the following concise form. Boldface x dot is equal to ax. What is a in our case? We just copy these coefficients. 3, -7, 9, or row number 1. 15, it's over here. Then there is nothing in front of x2, means 1. We put here 1. Here we have minus x3, means the coefficient is -1. Lastly, 7, 6, 7, 6, and there is no x2 term, means the coefficient in front of x2 is 0. We put here 0. Folks, think about questions.
What were the things that you said were equal again? Because you were pointing to like two matrices and you said they were equal.
So once again, please take a look at this. We start from this system. On the left-hand side in this system, we have derivatives. On the right-hand side of this system, we have linear combinations of x1 and so on xn. It turns out that indeed we can rewrite this system in this concise form because the left-hand side, according to what is written here, is a matrix column. The right-hand side, according to what is written, is a matrix column. Two matrix columns are equal if and only if the corresponding components are equal. Means this is equal to this, which is indeed equation number 1. And so on. This is equal to this, which is indeed equation number n. Was that your question?
Yes, thank you.
Other questions?
Yes, so does this simplification or rewriting only work with homogeneous linear systems with constant coefficients?
Well, coefficients don't have to be constant. However, our system has to be homogeneous indeed.
Okay, thank you.
If it is not homogeneous, then instead of ax, we put ax plus b, or if you wish, plus g, where g is the following matrix column: g1, g2, and so on, gn. Is this your question?
Yes, thank you.
Other questions?
So when we multiply the matrix A by the vector x, is what comes out, would we call that a vector on the right side? Is that a vector, or is that just a one-column matrix?
Well, note that a vector is a matrix column. So
Okay.
we can call this a vector, we can call this a matrix column.
Okay.
Now let us continue. Please take a look at these two definitions. In order to find the product of x and c, where c is a number, we multiply each component by c. Done. Definition number 2. When we add two matrix columns, we add the corresponding components. And now, theorem 1. Suppose x and y are two solutions of our system. System 6, it's over here, this, which is same as this. So consider solution number 1 and solution number 2. Remember, each solution is a matrix column. So boldface x is a solution, boldface y is a solution. Theorem 1 says that c times x is a solution again for any constant. b, x plus y is a solution again. Note that this theorem is very similar to one of the theorems that we discussed in class. Let us go back to algebraic properties of solutions. Over here, remember we discussed that if y1 and y2 are solutions of this homogeneous linear equation, then c1y1 plus c2y2 is a solution again. We can do same here. If boldface x and boldface y are solutions of our system, then if we combine a and b together, c1 x plus c2 y is a solution again. Folks, any questions here?
So, sir, basically by C, what you mean by Cx of t being a solution means that when you take the derivative of each of the terms and when you multiply it by x, it would give you a of x?
Very good question. So what is a solution of such an equation? Know that this equation can be rewritten as this. And by solution, we mean n functions, x1, x2, and so on, xn, that we arrange as a matrix column. But fundamentally, by a solution, we mean n functions, such that we plug in these functions into the system, and in each case, the left-hand side is equal to the right-hand side. Did I answer your question?
Yes, sir, thank you.
Other questions?
Could you explain what it means by the immediate corollary of theorem 1 is that any linear combination of solutions is a solution?
Very good question. So once again, if you compare this theorem with what is written here, in section 2.1, we immediately said that C1y1 plus C2y2 is a solution again. Here we split it into two parts. This is a solution and this is a solution. But now if we combine this and this, it's exactly what we mean by immediate corollary. If we combine this and this, we come up with the following result. C1x plus C2y is a solution of our system for any C1 and C2. Did I answer the question?
Yes, thank you.
So we are done with part number 1 and part number 2. Now part number 3. Let me show you how to solve systems of linear differential equations. Example number 1. Let us consider this system where A is 0, 1, negative 4, 0. Step 1. Rewrite this system in an expanded form. According to what is written here, the left-hand side is x1 prime, x2 prime. But now what is the right-hand side? In order to come up with the right-hand side, we multiply A by X. We use row-column rule. Row number 1 times this column. 0 times x1, 0 disappears, plus 1 times x2, which is x2. It's over here, x2. Row number 2, we multiply this by this. Negative 4 times x1 is negative 4x1 plus 0 times x2 disappears. This is how we come up with equation number 2. Next question is, how do we solve this system? Take a look at remark number 1. Note that this system is a particular case of this 2-by-2 system of differential equations. We can solve this system in 2 different ways. Way number 1. First, solve equation number 1 for x2 and then plug in the result into the second equation. Or solve equation number 2 for x1 and plug in the result into the first equation. Both approaches give same result. Repeat once again. Either we solve equation number 1, but not for x1. We solve equation number 1 for x2, and then plug in the result into equation number 2. Or we solve equation number 2, but not for x2. We solve equation number 2 for x1 and plug in the result into the first equation. You can ask me a question, what if we cannot solve equation number 1 for x2 and we cannot solve equation number 2 for x1? What do we do in this case? Well, note that we cannot solve equation number 1 for x2 only in one case, when b is equal to 0. Similarly, we cannot solve equation number 2 for x1 only in one case, when c is equal to 0. But if both b is equal to 0 and c is equal to 0, this term disappears and this term disappears. Now, if there is no second term here, this is a homogeneous, linear, differential equation with constant coefficients of first degree. We know how to solve it. If there is no here term number 1, this is again a linear, homogeneous, differential equation of order 1. We know how to solve it. So, if this is 0 and this is 0, solve this equation, find x1, solve this equation, find x2, which gives us the solution of the whole system. So, in a way, we can apply the method that we discuss in remark number 1 for any such a system. Now, what do we do here? Once again, in order to solve the system, either we solve equation number 1 for x2 or equation number 2 for x1. It is easier to solve equation number 1 for x2 because it is already solved for x2. We have x2 on one side, on the other side there is no x2. So in this particular case, equation number 1 is already solved for x2. Therefore, we just plug in this into the second equation. Here's how we do it. For convenience, let me copy the second equation over here. And now let us replace x2, it's over here, by x1 prime. Since x2 is equal to xy prime, we replace x2 by xy prime, we get this. But derivative of first derivative is second derivative. Lastly, we move this to the left and we get second order homogeneous linear differential equation with constant coefficients. We perfectly know how to solve it. We go back to section 2.2. Step 1, we write down the characteristic equation. We replace x1 prime prime by r square for x1 by 4. We move 4 to the right, done. We take square root of both sides. Negative 4 can be rewritten as 4 times negative 1. A root of the product is the product of roots. Square root of 4 is 2. We denote square root of negative 1 by I, and plus minus 2i can be rewritten as 0 plus minus 2i. According to what is written here, this is case 3. In our case, alpha is equal to 0 and beta is equal to 2. In order to find two linearly independent particular solutions of this equation, we use formula number 1 and formula number 2. Here it is, formula number 1, where alpha is 0 and beta is 2. Here we have formula number 2. 0 times t is 0. E to 0 power is 1. 1 times cosine is cosine. Similarly here, sine. Therefore, the general solution of this equation, x1, is c1 times cosine plus C2 times sine according to what is written here. This is x1. Question is, how do we find x2? Well, we go back to equation number 1. x2 is x1 prime. We replace x1 by this expression. Derivative of the sum is the sum of derivatives, and we factor the constants out. In order to find the derivative of cosine of 2t and of sine of 2t, we use the chain rule. The result follows. This is x2. Lastly, the solution of our system, boldface x, which is the following matrix column x1, x2, is equal to, we replace x1 by this, done, and we replace x2 by this, done. This is the general solution of our system. Now, we can rewrite this solution using these two formulas. According to formula number 2, this column can be rewritten as the sum of two columns. According to formula number 1, constant can be factored out. It's exactly what we do here. Step 1, rewrite this as the sum of two matrix columns. Factor out C1, factor out C2, done. So we got an analog of the previous theory. Note that as before, since we have a linear homogeneous system of equations, its general solution is a linear combination of two particular linearly independent solutions. Later in this course, we will show that these two solutions are indeed linear independent. Folks, any questions here?
So equation 10 is the general solution. Can we just stop there? Because is equation 11 just like a rewritten form?
Excellent question. Note that in order to solve a system of linear equations, it is not enough to find x1 only. We have to find both x1 and x2. You're absolutely right. This is the general solution, but of this single equation, we need the general solution of the whole system. Therefore, in addition, we need x2. So here is x1, here is x2. Therefore, this is the general solution of our system. By the way, you may ask me a question, how do we know that this is the general solution? How do we know that this formula describes all solutions of our system? Here's how we know. Know that this formula describes all solutions of this equation that we derive from this system. Therefore, there is no escape. Since x2 is x1 prime, this is the most general formula for x2. Therefore, this is the general solution of our system. Did I answer your question?
Yes, thank you.
Other questions?
Yeah, this might be a little silly, but how did you rewrite the two matrices into a system? Like not quite seeing it.
How do we rewrite this as this? Is this your question?
Yeah, exactly.
Yes, excellent question. So let me go back to what we discussed over here. Please take a look at this system, and please take a look at this. I claim that this can be rewritten as this. Actually, Let me go back to what is written here. Remember, I said that this system can be rewritten as this and vice versa. This can be rewritten as this. Why? Because both face x dot is this matrix column. A times x is this matrix column, and two matrix columns are equal if and only if the corresponding entries are equal. Means this is equal to this, equation number 1, and so on. This is equal to this, equation number n. In other words, if you compare this and this, in order to jump from x dot is equal to ax to the corresponding system, just copy these coefficients over here. In our case, the coefficients are 0, 1. Multiply 0 by x1, 0 disappears, plus 1 times x2, x2. Equation number 2, multiply negative 4 by x1, done, plus multiply 0 by x2, disappears. This is how we come up with this system. Did I answer the question?
Yeah, that makes sense. Thank you so much.
Any other questions?
Okay, just to make sure. Now that we do, now if we do x prime of t, so the solution that we have now is like c1 cosine 2t, negative 2 sine t plus c2. And now if we do x prime of t, that would be equal to a times x.
Yes, absolutely. If you plug in this, expression into the left-hand side and into the right-hand side, on the left-hand side, you take the derivative. On the right-hand side, you multiply a by x. The left-hand side will be equal to the right-hand side. Or equivalently, if you replace x1 by this and x2 by this here and here, the left-hand side here will be equal to the right-hand side here, and the left-hand side here will be equal to the right-hand side here after all simplifications. Was that your question?
Yes, sir. Thank you very much.
Other questions?
So I just have a quick question, right? So on the left, so right here, it's saying that x is x1 and x2, right? Like in the matrix. So then I understand how the calculations are done, but I don't understand how are we getting the x prime and x2 prime. Like I don't understand why it's like x1 prime. Like why is it not just x1 and x2, if that makes sense?
Very good question. Please take a look at this. Here we don't have boldface x. On the left-hand side, we have boldface x dot. Dot means derivative. This is what is given. The left-hand side of this equation, this one, is x1 prime, x2 prime, according to this. Note that if boldface x is this, boldface x dot is this. x1 prime, x2 prime, and so on, xn prime. So the left-hand side here is not boldface x, it's boldface x dot. So the left-hand side over here is the following matrix column: x1 prime, x2 prime. Does this answer your question?
Yeah, that makes a lot more sense. Okay.
Other questions?
And Professor, after you, so for like the last question that we were working on, right? After you separate into two matrices, right? So at the bottom of it, right? Afterwards, how would you like solve that?
We do not solve it. this is the general solution. We are done.
Oh, this would be considered the general solution. Okay.
Exactly. So it's written, it follows that this, and there are 3 different versions of same formula. Version number 1, version number 2, and version number 3. So this is a solution, this is a solution, this is a solution. This is version number 1, this is version number 2, this is version number 3. And now it's not just a solution, this is the general solution, because this is the general solution of this. Did I answer your question?
Yeah, that is. Thank you.